Every human face tells a story. Lines, angles, proportions. A lifetime of lived experience compressed into essentially geometry. What you're watching now is my face, being built line by line, not born, but printed. And in this episode of NexTech, we'll be exploring a world where anything can be replicated and what it means to make something. 3D printing isn't new. The concept goes back to the 1980s, but for decades it lived in the realm of industrial prototyping, expensive machinery, and specialized labs. What's changed is everything else: the cost, the precision, materials, and crucially, the imagination of the people using it. At its core, 3D printing begins not with plastic or metal, but with data. A set of blueprints telling a machine where to put material and where to leave it out. It's manufacturing stripped back to its most fundamental level. Hollywood understood the idea long before most manufacturers did.
How close are you guys?
We're just printing now.
That scene from Mission Impossible feels like science fiction. In 2026, it's closer to a Tuesday afternoon at a good fabrication center. Which is exactly why we're here at Plus 90 3D Digital, one of Turkey's most ambitious players in the additive manufacturing space. And before we start talking technology, it's time to get scanned. I'm trying to stand really still, but it's a little harder than it actually sounds. But these fine gentlemen are scanning me, every angle of my head, hoping to turn something very human into something very digital. What Ümit is doing isn't just taking a photograph. A camera captures light. A scanner captures structure, captures depth, dimension, and the precise contour of a surface in a three-dimensional space. Every ridge of the ear, every angle of the jaw translated into a point cloud of raw data.
Thanks to the scan we just performed, as you can see now, we're able to capture all the details. First, from here, you can see how the scan defines the subject using a heat map, showing which areas are captured with what level of quality. What you're seeing here is the raw data. After that, in its textured form, we can capture all the details. When we zoom in like this, you can see the level of precision. Of course, this can later be processed on a computer to produce a more refined image. What you see on this device is essentially the final output it can display.
Don't know if I want to see a very detailed version of myself here, but looks pretty good. Most companies in this space do one thing, either scanning or printing. But Plus 90 3D Digital has built itself around a more ambitious idea. They are a full-spectrum digital manufacturing partner. That distinction matters because the real complexity in this industry isn't the scanning or the printing. It's the decisions made in between, knowing which technologies to deploy for which application and in which material. The gap between prototype and a functioning end-use part can be enormous, and bridging that gap requires both mastering physics and economics. Özgür, when you're looking at a specific application, how do you decide between the different technologies, whether it's FDM, SLA, or metal manufacturing?
There is never really a preference. It's actually matching application requirements to process capabilities. So we start by finding the requirements or defining the requirements, functional requirements of the part. Is there any stress on part, any temperature or chemical constraints? Do we have a mass goal or a cost goal? So once we clear these questions, material options are naturally narrowed down.
Okay. We're in front of the design for additive manufacturing, which is a concept which is fairly new, I'm assuming. Can you give me a real-life example where design for additive manufacturing has made a product better, cheaper, more attractive for the consumer?
Actually, there's this project we did with an automotive company working on electric vehicles. And their goal was to extend the range of the car by reducing weight. So they approached us to redesign a seat for additive manufacturing. The original part here consisted of around 45 traditional manufacturing parts.
Okay.
But we redesigned it. We applied part consolidation and topologization and reduced the number of parts to just 4 pieces.
4 pieces.
And also we achieved 35% mass reduction.
That's no iteration. It's almost reinvention, and it points to something larger about where this technology is heading. Because companies doing most of the interesting work right now aren't printing parts as a replacement for traditional manufacturing. They're rethinking what a part should look like in the first place, unconstrained by limits of molds, tooling, or machining.
At Plus 90 3D Digital Factory, we guide our customers from the initial idea stage all the way to the end-use product. The defining feature of this digital factory is our ability to integrate multiple technologies rather than focusing on just one. For instance, you can combine additive manufacturing with traditional methods, or use additive manufacturing to create complex internal cores for parts produced traditionally. To give you an example, a traditional mold might take 12 weeks to produce. However, by using additive manufacturing to create the mold core, we can combine these technologies to deliver a finished mold in just 2 to 3 weeks. The real breakthrough is leveraging the inherent strengths of both additive and traditional manufacturing. When these two worlds meet, we produce parts that are superior in speed, quality, and cost effectiveness. This versatility is what distinguishes us from our competitors.
But you're moving from prototyping to real production. For companies who want to choose additive manufacturing, where's the tipping point? I mean, how do you inject that sense of trust?
That trust is built on the systems and certifications we use. We're Stratasys's partner in Turkey, and the materials we use are fully approved and certified. For example, the FDM systems you see behind me utilize specialized aerospace-grade materials like Altem 1010CG and Altem 9085. Furthermore, our facility is certified by the Aerospace Quality System and the Presidency of Defense Industries. This gives us the authority to provide parts for high-stakes aviation use.
One of Turkey's strategies is trying to establish itself as a regional manufacturing hub. Tell me where you feel 3D manufacturing or digital manufacturing fits into this general scheme.
Currently, additive manufacturing is already being used for end-use parts within the defense industry. While we're still working toward high-volume mass production, the future looks incredibly promising. In 10 to 15 years, when these technologies are fully integrated into a single machine, we will see a total transformation of end-use production.
Industrial certification and aerospace-grade materials represent one end of this ecosystem, but 3D printing has another frontier, one that's arguably just as consequential: the desktop or the garage, a world where the barrier between idea and object has all but collapsed.
So the critical thing is that with the 3D printer, you can create your beta product at the day one or week, and you can just sell it or give it to your target customer, and you can collect the feedback, and then you can also iterate it really fast. You don't have to spend the molding cost or design cost or other cost during this process. So This is like a living organism. So you are building something and people use it, and then you have to change it something. So you can do that really easy with these printers actually. And the material side and speed side is also much more advantage when you compare with the traditional methods.
That democratization or production is real, but it creates its own complexity. Because when everyone can be the manufacturer, the competitive advantage shifts to material quality, to machine reliability, and to expertise that turns a good print into a great one. NexTech understood this early. They don't just run a 3D printing farm, though the scale of that operation is impressive. They sell machines, they produce their own filament, and they take on custom jobs. It's the kind of vertical integration that gives them leverage at every stage in this industry, and that's difficult to match.
So what it enables us, becoming a biggest distributor of brands and becoming the manufacturer of the filaments, helps us reduce the costs, because essentially we buy the goods at a distributor price and we manufacture the goods at a manufacturer price. So the cost essentially decreases so much for us. This helps us reduce the cost for manufacturing, and it helps us become a competitive advantage to injection molding. That way we can become the next generation of injection molding, and for serial production this helps a lot.
Tell me, who's buying 3D printers? I mean, when you go back 5-6 years ago, it's the pandemic, everyone's stuck at home, you had these super enthusiastic hobbyists. I understand that, but 2026, who's buying 3D printers and what are they using them for?
So in the past, people are buying the 3D printers because it is an interesting hobby.
Yeah.
Right now, it's a tool for personal manufacturing at home. So before, in the past, you need to go to like a supermarket to buy your goods, plastics, and if you want to produce something, you needed to go to injection molder and let them manufacture the goods. But they won't be able to manufacture one of a kind of a good. But right now, at your home, in your room, sitting on a computer, you can already print something which is designed by other people, or you can let yourself design the goods and print at home. It's basically a personal manufacturing station.
All right, let me take it a step further. And I'm wondering if you guys are perhaps shooting yourselves in the foot in this respect. Because this has so much end user flexibility, do you see a model where production, even if it's not niche but mass production,
Yes.
is it decentralized, that we don't need production facilities, that everybody can actually, whatever they need, they determine it and they print it themselves? Is that a feasible model?
It is actually a very feasible model. Actually, what's best with 3D printing is you don't need production hubs at a scale, like 10,000s of machines running synchronized in like only one city. This way, you can let everybody manufacture the goods they want in their home. This is one of the solutions. Actually, we're not shooting ourselves in the foot. The way it is actually, we let them try and manufacture what they want, for 1 or 2 pieces or 10 pieces at their home. But when they scale it into a large manufacturing, that's where we come into play.
I'm taking a look here. I mean, this isn't plastic.
Yes, that's copper.
Copper metal. And tell me a little bit more about this then.
So, for example, this type of material is nearly impossible to manufacture with conventional methods like CNC or anything else. Subtractive manufacturing cannot put holes inside the metal, because that way this is more efficient for cooling. For example, this type of thing is manufactured with metal powder and laser printers, the expensive kind.
Yeah.
But the thing is, this enables the weight and the efficiency of the material is increased so much. For example, supercars recently using this kind of heat exchangers instead of the conventional ones. That way they have less weight and more performance in the same weight.
And it's not just the automotive industry. We're looking maybe at aerospace, defense, not just copper, but also
Exactly.
Much more advanced materials.
Yeah, for example, nuclear reactors are, the molten salt nuclear reactors, they are using this kind of heat exchangers to save the, space and the efficiency. And for example, the best of the thing is we can do this with the medical industry as well. As you see, this part is, suitable for chin replacement.
By the way, I mean, to portray how light this is. This
Yes.
actually weighs lighter than a paperclip.
Exactly.
In the healthcare sector, 3D technology isn't accelerating production, it's changing nature. The materials have evolved beyond plastic and metal and into biocompatible structures that can integrate with the human body. Anatomical models built from the patient's own scan data, so a surgeon can hold in their hands an exact replica of what they're about to operate on, which raises a question that's uncomfortable and important. In a world where machines can model the human body with millimetric precision, where does that leave the doctor? Kratos is a company that has bet big on answering that question. They work specifically in aesthetic surgery, and their platform uses 3D scanning and AI to do something that's never quite been possible before: show patients in 3 dimensions on their own phone exactly what they will look like after the procedure. Not a rough approximation, not a filtered photo, an AI processed and accurate model of their face, before and after. The man who built this is Emre Kaya, and I wanted to better understand how this changes the consultation room.
Normally, before that, the doctor is using the pictures. Before that, the doctor says to the patients, okay, please send me a picture, and we will do the simulation on it. But it's only just a profile picture. The patient's just wondering about how I will look like in the front view. And with this technology, the patient just see all the differences on their face. They just see everything on their phone in the 3D. The doctors do the simulation in their computer and they share with the patient. The patients see every detail on their phone. With this Kratos applications, they just see everything with their eyes. Everything they can decide with their doctor.
Okay, I understand they can see it, but they say seeing is believing. How real is the outcome, though?
To be able to get this real and picture, the first rule is we have to scan the patient's real face with all of the structure. And to be able to get this, it depends on our technology. With our technologies, we are taking pictures and also we are scanning, we are getting the video data, and we're just combining the depth data and also video and the pictures. All of these things come together and it creates the patient's real facial structure.
Seeing is believing, but surgery is still surgery, which is why the most thoughtful use of this technology isn't about replacing clinical judgment, it's about giving surgeons a tool to extend it.
We're entrusted with our patients' faces, and in surgery, achieving a high level of standardization is vital. The biggest advantage Kratos offers, which was my motto while developing this program with Emre, is serving as a digital assistant to the surgeon. Typically, a surgeon envisions a nose in their mind, perhaps shows the patient a Photoshop mock-up, and then goes into the operating room. However, a surgeon might be tired, or they may lack extensive experience. Usually, a surgeon relies on their own intuition and aesthetic perception. Kratos changes that. The program analyzes the patient's before and after states and provides a precise surgical roadmap in millimeters. If I take these metrics into surgery and set aside my subjective perception and follow the data Emre and the program provide to adjust cartilage and bone, the result is 99% identical to our simulation.
I wanted to see this in practice, in a hospital with a real patient on a real day. So we were invited to follow the process from the first scan to the operating table.
Hastamızın 3 boyutlu taramasını yaptık.
We've just completed a 3D scan of our patient. What makes this data so valuable? We've transferred the exact dimensions of the patient's nose to the computer with millimeter precision. While there are many programs that perform 3D scans, our software uses artificial intelligence to translate those physical dimensions into a digital space perfectly. Because I have these exact measurements, I can accurately compare the current nose to the new nose I'm about to design in Photoshop.
Böylece
Instead of guessing, I can say, to achieve the look the patient wants, I need to lower the nasal bridge by 3 millimeters, lift the tip by 10 degrees, and narrow the nostrils by 4 millimeters. Rhinoplasty is often full of surprises. When we tell a patient we will lift the tip, my definition of slightly might be different from theirs. This AI support eliminates that uncertainty. I show the patient the exact degree of the lift, and I execute that exact measurement in surgery. Now let's look at the Photoshop simulation. We've designed a nose that fits this patient's face. We've removed the hump, kept the tip height natural, and corrected the nasal deviation to bring it to the midline. The work of the future starts here, because not every doctor has the artistic hand of a Picasso, or they might be less experienced. We developed this program to remove subjectivity by overlaying the old nose with the new simulation. The program gives me a millimeter by millimeter guide. I'll present this to the patient now, make any minor adjustments they desire, and then head into surgery to perform a truly precision-guided operation.
The patient is Jeremy, and he's just flown in on a 12-hour flight from Canada, which tells you how seriously people are taking the precision this technology promises. The simulation is done, the measurements are locked, the surgeons know to the millimeter what needs to move and by how much. And now the conversation ends and the work begins. What started out as data, measurements, scans, and a digital version of a future face now is in the hands of the surgeons. In just a couple of hours, no thanks to 3D modeling, Jeremy will wake up to a new facial feature. And after a successful surgery, the results speak for themselves, and perhaps more importantly, they match. But 3D modeling doesn't stop at the human body. In fact, one of its longest running applications has nothing to do with manufacturing, medicine, or materials science. It lives inside a screen, and it has been quietly raising the bar for what we consider visual reality for decades. We're talking about gaming, and the company that's been doing some of Turkey's most ambitious work is Motion Blur. I asked their CEO, Kadir Demirdan, a simple question. Just how advanced has this sector become? So we're talking about motion capture. In essence, it's transforming human motion into digital data. How important is the detail or the exactness or the perfectness of the human motion for the final product?
Motion capture has been around for a long time, evolving from camera-based systems to the wireless suits we use today. However, there is often a translation issue where data loses fluidness when transferred to the computer. Because of this, mocap data still requires a human touch. To reach perfection, you need two things: top-tier equipment and expert animators. You can't rely on the machine alone. For example, if we want a character to perform a superhuman feat like jumping 5 meters in the air to kick, we record a real actor performing a normal kick on the ground, and then an animator translates that movement into the air. We can't distinguish 3D characters from real people in movies today because the underlying movement is human, but it is the animator who polishes that data into something flawless.
When you look at Hollywood films, amazing stuff you see on screen. The fact is, a lot of that is actually pre-produced. The crux here, the trick here, is to do this in real time, isn't it?
There is a fundamental difference between a movie and a game. In a movie, the scene is static, the director chooses the angle, and it never changes. In a game, the player has control. I can look up, down, left, or right. The scenario is constantly changing based on player input. In game development, we have in-game cinematics, which are similar to filming a movie scene with set frames and lines. Everybody is happy because it's controlled, but the moment you give the controller back to the player, the job becomes much harder.
So essentially, it's variable change in real time. Do you see any application outside of gaming where this has a future potential?
Evet, çok büyük bir potansiyeli var.
It has massive potential. We're already seeing virtual production in shows like The Mandalorian, where they use real-time game engines to render backgrounds during filming. The game industry is multidisciplinary. To build a world, you need to understand cinematography, lighting, AI, pathfinding algorithms, physics, and UI design. All these fields are benefiting from real-time tech. A supercomputer from 10 years ago is essentially the desktop you use today. Without the demand for real-time rendering, we wouldn't have this level of hardware. Beyond entertainment, this technology is vital for everything from military simulations to AI communication.
İlgili modelleri bilmeniz gerekiyor.
One of the most elegant solutions Motion Blur deploys is part human and part digital: motion capture. The idea is deceptively simple. Suit up a real human, record how their body moves through space, and feed that data into a 3D environment. The results are movement that no algorithm could convincingly fake. We've seen how 3D technology is transforming everything from manufacturing and design to digital worlds and human identity. It is a world where reality can be scanned, reshaped, and rebuilt. And to tell the truth, sometimes even better than before. And maybe that's the real story here. Not just what we can make, but how far we're willing to blur the line between the real and the possible. The tools are here. The capabilities are growing fast. The only question is what we choose to build next. Well, that's it for this edition of NexTech. I'm Ali Can Ayanlar. Thanks for watching, and we'll see you next time.